In today's demonstration, we will be seeing 3 different lifting methods and some convenient techniques for pre-processing such analyses. Finally, there will be some allowance for questions and answers in the end of our meeting. All meetings are recorded and they can be retrieved later from the Bentley server. So without spending any more time, we can look at the agenda. Today's meeting is divided in 3 parts, where we will discuss 3 semi-automated methods to set up a lift analysis. In the first model, we're going to discuss the pre-processing steps in the analysis workflow for a single spreader bar lift analysis. And we will also see how easy it is to add additional slings in our model. In the second model, we will be seeing the pre-processing steps again and the analysis workflow for a double spreader bar lift analysis. Finally, in the third model, we will be seeing the pre-processing steps and the analysis workflow for a lift with a pulley assembly. The lifting arrangement of all 3 methods can be seen on the right-hand side of your screen. So here we have the single spreader, double spreader bar, and the pulley assembly. Let us look at the first set of files. Each analysis will have a set of files that come with it. The single spreader bar is defined, and after we have sling elements that are created between the pad eyes and the spreader bar. The pad eyes are nodes in our model. So if we switch over to Moses Executive now, look into the model, everything we will be seeing today is in the new Moses Executive interface that was released last month. This is a new interface known as Moses Executive. It is currently in the technology preview stage, and although we still carry out some tests on it, it is available for you to use. It's a modern graphics interface that improves navigation, streamlines the modeling experience, and facilitates post-processing, as we will see. Today's files are all opened in the project window here, so I can conveniently sweep through these files. So we will be starting with a single bar SIF. And the syntax in the code remains as before, so there's nothing new for you to learn there. And we go through a set of commands that bring in the model, which has been converted from a SAX file. And then we have any additional commands that follow. We define a bar, we call it bar A, and then we specify a length. It's of a tubular cross section with these dimensions, and then we create some points in the X direction, which is the length of this bar, and then through a set of loops and points in S1, S2, S3 that are defined in the lift.dat. You see how convenient it is. I can double click on the lift.dat, and all the associated files that come into my analysis are branched underneath the command file. So in there I have the other parameters that I'm using in the analysis. So back to the command file. Through some operations, I'm getting to create the bar nodes that I have specified in my analysis from where the pad eyes will be. And then with the use of the connector command, I'm getting to, after I have defined a class for the slings, whose dimensions can be seen here, and properties. For each and every pad eye, I can set up a connector between the bar and the pad eye. I'm repeating this 5 times, as many as the hook number in my bar, and then I'm getting the configuration of this system, forces in my connectors, and I have a routine here that is asking the user whether I want to, if that is a project requirement, to rotate my model by 30 degrees in this case with respect to the z-axis. This could be 15 or any other number that the project requires. In this example, we won't be making use of it, but it is an automation that is provided in this file. And then we get the configuration of the system and go on. For facilitating convergence, set to ignore motions on the bar in XYZ and rotations, and when we get status F connector, the forces on the connectors out. If you wish, you can carry out a time domain analysis if you want, if your project requires. In this case, I have an environment that looks like this, certain sea state, some wind, and then I'm going on to do the time domain analysis and then get out some results out of this system. So if I were to, the right-hand side here is the log window, the terminal. If I were to run this analysis, I would click here. The system will go and process the CIF file and the DAT file. This is not fully supported, as you can see, because we are looking at a technology preview version of Executive. This is what the routine is asking me, whether I want to rotate my body by 30 degrees, as we saw earlier on. So I can set to no. And the analysis carries on. Enter the time domain analysis and then get out whatever I'm asking in the structural, from the structural part of the analysis. That's a code check, as you can see here. So we can take the logout file and go to plot and results. Anything I have requested with the CF magnitude command is a new tab that I have here. And I can go in the filter column. One is a connector, select values. Here I had, remember, 2 connectors in place. So as a function of time, I can get to see what the magnitude on these 2 connectors is. If I were to also plot the model would look like this. Is a tripod jacket. Looks like this. I can animate this over time. Neat. Really, nothing's happening. It's just hanging there. And if I were to click on any of these slings here, I would get to see this is sling LS111 or LS511. So this is what we get to see in this plot. Now, another thing I wanted to demonstrate is if I go back to the lift dat, remember this is the data file associated with my command file. And here is where I specify these variables padi1, padi2, and so on. And I can, as long as I know where the padis are located in my model, I can type in some additional nodes if I were to add 2 additional slings. So if I make this 8001 for padi2, padi4, make this 6001, save, clear the previously created results, and rerun. This time I'm creating 2 additional slings, so I will be having 4 connectors in my model. The solver again enters the time domain analysis and solves. Okay, now going back to, let's see how the model looks like. I have added node numbers. I have a different arrangement this time. See, with 4 connectors. And when it comes to the CF magnitude command, I can go in here to get the other 3 forces on my connectors. So again, I can see how they behave over time. You can see at the this is a very convenient way for adding or removing connector elements from your analysis. So this is all as far as a single spreader bar is concerned. The second set of files I would like to demonstrate today is the double spreader bar. Again, this is a semi-automated method for setting up a lift with a double spreader bar this time. We have 2 spreader bars, as in the figure right-hand side. And in a similar fashion, sling elements will be defined again between the pad I nodes and the spreader bars. In addition to what we saw in the first example, we will be having a spreadsheet in this method that makes things slightly easier for us to visualize the setup. If I switch back to executive, that file, double bar SIF. So remember I mentioned at the beginning we have all the files for today here. And I can right click on double bar SIF and make that a primary SIF. So if I were to clear the results or run the results, then the solver would read what is happening here. If I overlook this step and I clear or run, then the solver will be running with the last defined primary file, which was the single bar. So keep an eye on this. We'll be working on the double bar SIF, which is this tab here. Let's suppress plot and results for now. And let us spend some time on how this set of files was created. I have a spreadsheet here which facilitates setting up this example. It's very easy to follow, and it may take some time to wrap your mind around it, but it is convenient as long as you become familiar with it. We have in this sketch here, this is a side view of the bar. We have in this example here 5 or fewer hooks if we wanted to, and then we have the length 1, length 2, length 3 parameters along the length of the bar. So in this example here we have 2, 5, 13 and so on meters. This is a dummy object that we're going to lift. We have bar A and bar B. And what we have here is PP1, port pad I1, port pad I2, and so on. And on the other side, we have starboard pad I1, starboard pad I2, and so on. So this is where we specify the pad I nodes. Again, these are nodes that we know from our model, wherever the model is coming from, SACS, third-party or natively created in Moses. So we know the number of these nodes. We put them in here. In the second tab, we have bar B. Bar B is this bar this time. Again, of the same geometry or of different cross-sectional properties if we wish to. But in this example, both are the same. Both have the same cross-sectional properties and length. Again, we choose to have the same length for the hooks and different node numbers this time because we will be using port pad I4, port pad I5, starboard pad I4, and starboard pad I5. So these are the numbers. Another variable that another two variables that need to be set up is the elevation plus minus relative to bar A. This is what we have here. Choose to have it 5 meters to place bar B 5 meters above bar A. And the spacing between them, we also specify it to be 25 meters. If we wish to do so, we can edit these two cells. Again, this is a side view. When it comes to the export tab, all the previously defined cells in the first 3 tabs have been transferred over to this tab here. So this is the input for the lift from lift XLS X, which we will right-click copy into Moses. So what we have here is the bar height, this is bar AZ coordinate, all the lengths for the 2 bars, and a user-defined command here that looks like this is set pad A2. So pad is the first 3 letters of my command. Then I have the bar name at which these 2 nodes correspond to. So these 2 nodes I know that correspond to bar A. And then the hook number is hook number 2. Remember the hook number is defined, is shown here. So this is hook 1, hook 2, hook 3, and so on. And then in the penultimate tab, remember we've specified the span between the bars and the elevation relative to bar A, which we can see here, and the hook position in bar B. And remember, again, it's the same methodology, the same rationale. The first three letters of the command, B, relates to bar B, and the last number is hook number. You can see the syntax of this command. So if I were to select all this grayed out area, right-click, copy, and bring it in here, I can right-click and copy everything that I had in my Excel spreadsheet. This now will become the input, the data file for the double bar command. So I get to bring this and read everything in through in line 008. Again, it's the same setup, whatever you have in your project that you choose to factor up or down. And we create the two bars. And through some manipulation, we position the bars. We have as many hook numbers as we had in the spreadsheet earlier on. And then for each and every one, we have a loop in position to create the connectors between the nodes and the hooks. Describe body cargo, and then we have connector forces and the configuration of the system. Again, for the sake of easing convergence, we ignore motions in the two bars. We get connector forces status again, and then another environment, which is not necessary, but for the sake of this example here, we have some C state, wind acting, and 100-second analysis time. If I were to rerun this, clear any previously created results, rerun the double bar SIF. Remember, I have right-click here, and I made that my primary analysis file. So this runs now. Okay. And this is how my model looks like right now. I had two bars, bar A, bar B. From what I had in my spreadsheet, I had defined 8 nodes, 2, 4 for bar A, 6, 8 for bar B, which I can see back here. Next, I can process the connector forces. No longer need for any commands because everything that I have asked Moses to do has already saved, and I'm simply accessing the database here. If I go here and select, let's say, connectors LSB 511, B111, A211, and so on, I can get to see how these forces have behaved over time. If I were to select all 8 of them, I can select all or suppress some of them and choose whatever I need. I get a corresponding plot of the behavior of the forces over time. In the last set of files, we'll be looking at a Pulley assembly. This again demonstrates a semi-automated method for setting up a lift with the Pulley assembly. In this example, we have pulleys, and in a similar fashion as before, sling elements are defined between the pad nodes and the pulleys. Unique to this example is the use of assembly pulley command, documented in the reference manual if you wish to know more. And as before, we have the connector elements here are of SLLM type. In essence, an assembly pulley assembly is a single line passing through n-1 number of pulleys, where n is the number of lines. So if you have this kind of a setup, you need to use the assembly pulley command. If we go back to executive, this one, I'm interested now in the lift pulley, I make this my primary SIF. This is how it looks like. Okay. What is specific in this type of analysis is that I have a number of nodes in XYZ. This is something that I know or I choose to set up. In this example here, they come from SACS, so I know where they are in space. specified. I make that body ground so that the lift is fixed with respect to these points. I position my deck accordingly. I create a class. These properties. I set up connectors. I call them A, B, C, D, E, F, G, H. And then I define the nodes. Part 3, U3, for example. I set up a line tension equal to the lift object weight divided by 8, so that I'm somehow creating some kind of balance over these connectors. And then I'm using the assembly pulley command. This is the name of the first assembly. I call it a pulley port, and I specify the number of the elements, connectors A, B, C, D, the first 4, and then I have pulley starboard, and I choose to put in there the last 4. Also in here, I had the dot file, which I'm bringing from my directories. I specify where the model is. This is a converted Sachs model. If you don't have a converted Sachs model, it could very well be in the same directory, and you would simply use the insert command. So this is how the CIF file looks like. And if I were to rerun this analysis, I'm having some warning message because some of the nodes that come from the converted Sachs model have features that are not fully supported by, so worry about. And, okay, the analysis has I can go plot my results. Okay, this is what my model looks like with the 8 connectors up at the pulleys. And okay, for some reason my nodes are not okay. It's been reported out file. Remember, this is a technology preview, so from version 11 that has not been released yet, so we're testing the software. What we had here in the out file is connector forces are requested, code checks in 2 sets. First for unit duration between 0 and 1, it's the end. In this case, we don't have these limits. Run this one last time. That changes it. Okay, I can apologize for this, but what we would expect to see here is again connector forces as a function of time. A similar graph as the first 2 that we saw. What these connectors did here over time. So if I click on any item in here, I have the properties window. This is again something that you may not be aware. And if I were to click on any item that I see in my model window, I get to see its properties here. So this would be of this class, and this is the connector H. Remember, in my CIF file here, I have created connector H in line 35 that goes from JPAD 0 to JDU10. This is up here. JDU10 has these coordinates where the pulleys are located. So this is connector H. And I think that brings me to the end of what I had to show you today. If there are any
Yeah.
questions,
Spiro,
be
can I
happy to.
interrupt?
Yes, go ahead.
We do have a question.
Mhm.
I think it has to do with this last analysis that you were doing.
Yes.
Okay. Um, I saw that you used two assembly pulley commands. You define the
Mhm.
port side before the starboard side. Does it always have to be in that order?
Yes, this is what we see down here. No, it's not specific. The way we um, define these pulley assemblies is not specific to any order. It could be the starboard first and then the port, or as you see it on your screen. So the analysis is not sensitive to the way that, or the order at which we define.
Okay, and I think this next one also has to do with this analysis. I'm looking at the orientation of the deck, so I think this person's also looking at the orientation of that deck.
Mm-hmm.
Okay, what happens if the center of gravity is not at the geometric center of the body?
Um, if it is minor and slight, uh, I mean, you can visually confirm what the system has done through this window here. So we do get to see that there is a small rotation or a tilt. To find out the exact angles um, for this analysis, you can use the status F connector. That's one, and you would see as it is in this case an equal force distribution per connector. So not all 8 of them in a symmetric model like this. Not all 8 connectors would receive the same force. And in addition to that, with the status F connector, the equi command would also report the rotations with respect to the 3 axes. So you can get to see exactly what this angle is. This, having asked that, this model, although it looks symmetric, is not, because it's a converted Sachs model, and there are some associated loads on these beams that we do not see here. So we don't simply lift a bare beam structure. You see there are loads imposed on them. Hence the imbalance that we see here. This is where this imbalance is coming from. Although it is deceiving because it is a symmetric structure. When it comes to the loads, if I were to strip the loads of these beams from the Sachs model, then it would be keel position, let's call it. I hope that answers your question.
Spiro, I think these next
Yeah.
two questions are from a experienced Moses user, somebody who has done some lifts with Moses in the past. Okay.
Okay.
Um, I am u- I am used to doing lift analysis with the tip hook assembly. How does that feature include the weight of the hook?
Okay. Um, we do not model the hook explicitly. Usually, this hook weight is very small in comparison to what we lift. If the weight is significant, we can choose to make a separate body and assign properties to it. Alternatively, um, if you don't want to add to your model by going into trouble and creating new bodies, you can factor in the weight of the hook, and then this you can do with the margin option in ampersand apply command. So there is two ways here. You can either model it as a separate body or factor in that weight to the rest of the structure.
Okay, and I think this might be the same person. Um,
Okay.
what's the difference between SL underscore ELEM, so the sling SL element, and then the sling element? So I see in this file you have right now, you are showing the SL underscore ELEM.
Yes. In all three examples, I use the SL underscore LM element. There are some minor differences between the two, the SLLM and the sling elements. The SLLM are used to connect bodies, while the slings cannot do that. They don't have this property. Slings are also using the tip hook assembly if you want to. Another difference between the two families of elements is that with the SLLM, you can add self-weight, while the slings do not have this property. They are weightless. So depending on what you want to model or what the specifics are of your problem, you can choose one of the two. So in all examples, in all three examples, I was using the SLLM family of elements.
Okay, and it looks like people are liking your files. Can we have a copy of these files?
Yes, these set of files, the SIFs and the DATs, including the spreadsheet that I showed you here, are available for you. I believe Ali can communicate these to any interested parties. So these are available for you if you're interested in having a copy.
Okay, and so we're presenting this last one, and then the one with the spreadsheet. This was an automated way of doing the spreader bar.
Yes, the last
Uh-huh.
example did not include or did not necessitate the use of the spreadsheet. The spreadsheet was for the double spreader setup.
Right. But you could, in essence, use the same concepts.
Yes, that's right. Yes, you could do that. I found personally the setting up the double spreader analysis far more challenging than the pulley or the single spreader bar. Hence the conception of this figure here that shows what the command is and what you need to put for every connector that went from hook 4 in bar A to these two nodes. I believe if you study this for a while, it will become very clear or very easy in setting up. If similar analysis, if I were to use port PADI 3 instead of port PADI 4, all I had to do was to use PADI 4 0904. I would go in my SACS model or wherever my model is coming from, query what the node number is in PP3, port PADI 3, and type in here the corresponding node number. Then I would go in my export tab. This node here is coming through. Remember, this grayed out area, I highlight it, right click copy, and then I paste it in my lift set dat file. All this is the paste result of what I had in the spreadsheet. And this one here would have a different number. If I were to do that, then the resulting arrangement would be what I have here. But this connector would go from hook 4 in bar B to port PADI 3, or any other node I have in the model, wherever my PADIs are located.
Okay, and this looks like there's lots of people doing lifts. In my recent project, I was asked to perform a transient analysis. A transient analysis is modeling the accidental breaking of one of the slings. Can I model the transient in Moses?
Yes, if you were to account for accidental breaking in the time domain, you can use the deactivate option available in the assembly tip hook definition command to deactivate either a series or a specific connector in your analysis. You can do that either before or during the analysis to see what the effect is on the rest of the connectors and what the motions, what the position of the lift objects will be. So yes, you can do that by using the deactivate option. If for any reason you want to remove one of the connectors during or before the analysis.
Okay, and it looks like somebody's really paying close attention.
Okay, go ahead.
Okay, I saw that you used the and channel command.
Yes.
Why did you want to redirect part of the output?
Yes, that was in the last example here, this one here. It may or may not be a project-specific requirement. It is for convenience only. If it is necessary or preferred in case where you have multiple solutions from one analysis, you can send them to different directories. In this case here, I'm telling Moses where to put the results, and if I were to do that, then I have as input dot lift Moses, and in there I have load cases that have been created as a result. So if I were to follow this path in my working directory in assembly, here it is. And if I were to open this, this is what I would see in there. So Moses has created these load conditions that I can use afterwards. But this may or may not be necessary for a project. I only wanted to show you that you can use this channel command in your analysis. Some of you may already know it and have used it before. To some other users may be.
Okay, and this last one, we'll see if we get more. Starting to not be as frequent. In my recent lift operations, we used a passive heave compensator. Is there a way to model a possible heave compensator? I think they mean a passive heave compensator.
Yes, there is. We are preparing a meeting similar to this one that we have today in the new year, where the passive heave compensators will be discussed. It's a whole new chapter. It's a different subject. We are aware of this need and we're addressing it. I would say stay tuned for more, and yes, you will be hearing from us very soon about covering this topic. But this is something that we are aware of and Moses can address.
Okay, and one more, Spiro. I think they're talking about line 37, the ampersand connector minus L tension. How are the sling lengths determined? And I think that's right there on line 30.
Originally, yes. Originally, I had specified a class. I called it wire of this type of elements, this diameter and this length. By using this, I changed the tension in the length in my connectors so that the resultant tension is equal to this amount. This is there is no right or wrong. I could either leave it out and have whatever the tension is on these 8 lengths, or use this option here to control the length and the tension. So it's not specific to this analysis. It's an attempt, let's say, to control what how much tension the connectors are seeing.